So I've picked out a few. They're highlighted here in yellow to be representative of what you can expect on an exam. So we'll go through them. They're about 100. So we're going to have to take, some of them are going to be really quick because a few of them take some time to work out. But you can still stop me at any time. If you remember something that gave you trouble and you just didn't think of it now. All right, let's take them in order. The first people to attempt to explain why chemical changes occur were the Greeks, right? The ancient Greeks. They tried to explain it. I mean, they missed the mark pretty far, but they made an attempt. The first chemist to perform truly quantitative experiments was, and I know the answers are up there. Try to think of them on your own. Robert Boyle. Robert Boyle ran quantitative experiments, which was not customary of the day. They were still living under the chef's concept of chemistry, the alchemists. You learned how to do things from as an apprentice, from the master, and then you continued with those and tried to improve on them. But quantitative, at most, the alchemists were semi-quantitative. You know, a dash of this, a cup of that. So that would be Robert Boyle. The scientist who discovered the law of conservation of mass and is also called the father of modern chemistry. Antoine Lavoisier. I always remember him because he lost his head in the French Revolution. I guess his wife survived. They don't mention her. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? This is one of those, when you say proportions in a law, students tend to get this one mixed up with definite proportions. Definite proportions, remember, it just says no matter where the compound comes from, the elements in the compound are going to be the same ratio by mass, no matter where they come from, whether it's water from rocket burn or from purification of salt water. That water is still going to have the same ratio of hydrogen to oxygen. But the law of multiple proportions says that when you have a binary compound, or you have an element here, let's see, this is 4. You have 2 elements, but you have different compounds made of those same 2 elements. If you standardize one of them to unitary value, and this is ratio by mass, then the ratios of the second element will be in whole number multiples. So say, and this is the way we understand it now. If we can standardize this one to say, I don't know, 3 grams. And then this one will be, since they're different weights, right? Atomic weights, since they're different, then we can say maybe this one is 6 grams. Well, that means if we standardize this one to 3 grams, then this one is going to be twice that. This is going to be 3 times that. Okay. That's what multiple proportions means. So in order to illustrate that law, you have to have only 2 elements, right? And they have to be in whole number multiples of one another. So A can't be it, right? Because one of them's got chlorine and the other one doesn't, and one of them's binary and the other one's not. B can't be it for similar reasons, right? You've got an element in one that you don't have in the other. C, similarly. D would be a good candidate because you got nitrogen in both of them and oxygen in both of them. And in one of them, there's only one oxygen per molecule, and the other one, there are two oxygens per molecule. That gives you the whole number multiples. Okay, that's why D is the answer for this one. Wait a minute, not five. Skipping down to 7. A sample of chemical X is found to contain 5 grams of oxygen. Okay, chemical X is 5 grams. And I find that extracting information from word problems is the best way to eliminate some of the confusion. If you try to solve a word problem, and word problems are designed to do what? Confuse, right? So if you extract the information and put it in a form that's recognizable, then it tends to make more sense. And 10 grams of carbon, okay? And everybody's memorized their symbols, right? Or you're at least working on them. Okay. Let's get this out of the way so I can see what I'm doing. And 20 grams of nitrogen. Okay, that compound has that mass ratio of each one of these elements. The law of definite proportions would predict that 70-gram sample of the chemical would contain how many grams of carbon? Well, what's the total weight here? If it's got 5 grams of oxygen, 10 carbon, and 20 nitrogen, the total would be 35, right? That would be the total. What if we double that mass to 70 grams? What's that going to do to the rest of them? Right? It double that one, double that one, double that one. So if you want to find the, let's see, grams of carbon, you just double the grams of carbon. Okay. Right. Number 9. Which of the following statements from Dalton's atomic theory is no longer true according to the modern atomic theory? Elements are made up of tiny particles called atoms. Yeah, that's still true. Atoms are not created or destroyed in chemical reactions. That's also true. All atoms of a given element are identical. No, because we know about isotopes now. So that was definitely wrong. And then if you have wonky ones at the end, like all of the above, 2 of the above, and that kind of thing, that means you got to go through all of them to be sure that you have all the correct answers. So D says atoms are indivisible in chemical reactions. That's also true. And that's another way of saying, that's another like corollary to B. So when C says all the statements are true according to the modern theory, that's not true. Right. So C is the only possibility there. Let's see, number 11. The chemist credited for inventing a set of symbols for writing elements and a system for writing the formulas of compounds, and for discovering selenium, silicon, thorium is. We didn't talk about this in class, but I know it's in your textbook. Right? The one who's responsible for the method of representing elements is Berzelius. He was a Swedish chemist. And there were a couple, 3, 4 maybe, possibilities for representing elements. Robert Boyle had the really, his was wild. I'm glad he didn't win. So you have to memorize separate weird symbols. This makes a whole lot more sense. Just the first letter or 2 letters, not always of English, but some of them are Latin. Like what? Na. What's that? Sodium. Right? It's from the Latin natrum. K is from the Latin kalium for potassium. Okay? So don't get it confused with P, which is potassium. I mean, phosphorus. Okay. 12. Avogadro's hypothesis states that, okay, you got one definition, and then I showed you an example with the circles, like the volumes. If the pressure inside each vessel is the same in each one, temperature is the same, volume's the same, then what has to be the same? Number of particles. I think that's the best way to represent it. But in words, at the same temperature, well, that is. I gave you that definition right there in 10. Right. There are other definitions, but I think that was the best. It's the most useful. And we'll probably get into that chapter 3, I think, where Avogadro's hypothesis got chemists out of a really sticky situation in latter 1800s. 13. The first scientist to show that atoms emit any negative particles was Thomson, J.J. Thomson. Remember with his tube? Yeah. And what else did he determine? The ratio of mass to charge for an electron. He didn't give us the mass of the electron, just the ratio of the charge to the mass. That was used later to determine the mass of an electron. 14. Many classic experiments have given us indirect evidence of the nature of the atom. Which of the experiments listed below did not give results described? The Rutherford experiment proved Thomas' plum pudding model of the atom to be essentially correct. Well, that's false. Rutherford told us what? Rutherford proved the nuclear model, right, where most of the mass of the atom is in the nucleus, where what particles reside? Proton, neutron. And the rest of the space of the atom is occupied by very, very light particles, the electrons. That's what Rutherford actually showed us. And in the interest of time, I'm going to skip the rest of them. 15. The scientist whose alpha particle scattering experiment led him to conclude that the nucleus of the atom contains a dense center positive charge. All right, we got that one already. That's Ernest Rutherford. 2 for the price of 1. 16. I think this is also a continuation. Alpha particles beamed at thin metal foil may what? What did they actually do when Rutherford did the experiment? Most of them went straight through, right? Which says the atom is largely empty space. What also happened? Some were slightly diverted and struck the detectors with just a slight angle of deviation. Some of them came almost straight back at the target. I mean, at the source of the alpha particles. So all of those are possible. A, B, and C are results of the experiment. '17. Which one of the following statements about atomic structure is false? Okay. When it says that means you got to go through all of them. An atom is mostly empty space. That's true. Almost all the mass of an atom is concentrated in the nucleus. That's also true. The protons and neutrons in the nucleus are very tightly packed. Well, yeah, they have to be. There's a density factor. There's only so much room in an atom, and if most of the atom is empty space, then the protons and neutrons in the nucleus have to be packed really tight. So where's the issue with that? What's the charge on a proton? Positive, right? When you pack positive charges close together, what are they going to try to do? They're going to try to fly apart, right? Reject one another. So there's a force that's been proposed of the four fundamental forces in nature. The one that holds them together is called the strong nuclear force. And it's believed that it's mediated by the presence of neutrons. So you have to have the neutrons there to keep the protons from flying apart. Now, there are theories about how that happens. One is that there's a particle that's exchanged between neutrons and protons. So the particle goes from a neutron to a proton. Now the neutron becomes a proton and the proton becomes a neutron. That's one possibility. But be that as it may, as the nucleus gets bigger, what you'll notice is, say we're looking at oxygen, it has 8 protons. So what's one isotope? The most common isotope of oxygen has 16 nucleons, like 8 protons, 8 neutrons. So the smaller nuclei have roughly equal protons and neutrons. But as the nucleus gets bigger and bigger and bigger, you're going to find you need more neutrons to hold the nucleus together. And that's because the distance of interaction of the strong nuclear force is very short. So if you have just equal numbers of neutrons, you're not going to have enough of them in the vicinity of to keep it from blowing apart. Okay. So for instance, you have uranium with 92, but it's got 238 nucleons. Right? So a lot more neutrons required. Okay. I wasted too much time. 20. Okay, which of the following atomic symbols is incorrect? Okay, if we have carbon, chlorine, phosphorus, potassium, and nitrogen, I think is the last one. Yeah. The first thing I would do is say, I know that symbols and numbers, the atomic number, go together. They're joined at the hip. So if I see carbon and I look up there and the atomic number is 6, then I look at this one and say, okay, 6 is right. Now the mass number might be wrong, but maybe I can find the wrong one here simply by going through the atomic numbers. So chlorine could be 17. I'll look there, 17. Phosphorus is 15. I'll look there, 15. Okay. Potassium. Look over there. Potassium is 19. That looks good. And nitrogen is 7. And I look there. Nope. They say it's 8. That's wrong. So we got to the answer really quick just by looking at atomic numbers. Now, if all the atomic numbers are correct, then you got to go back to the mass numbers and see if they jive. So if you're looking at your periodic table, what do you notice about those numbers? None of them are whole, right? That's because of weighted average of isotopes. But you can usually pick out the most common isotope. For instance, we were looking at oxygen before, 15.999. That means that the most common isotope is 16. Right? And the only reason it's a little less than 16 is because we have a few oxygen 15s that bring the average down. But the most common one would be 16. Okay. Now, there are a few squirrely ones in there, like chlorine, 35 and a half. So we figure that 35 and 36 are roughly equal isotopic abundances. That's why it's that value. And there are a couple of others that do that. But most of them are really close to the most common isotope. All right, that was 2021. All right, the element rhenium. You didn't have to memorize this one, but rhenium is transition. Where's R? There it is, 75. So the element rhenium exists as 2 stable isotopes and 18 unstable isotopes. Rhenium-185 has in its nucleus, it's 185 here, and rhenium-75 here. That's the one we're talking about. That other stuff where they say exists as 2 stable isotopes and 18 unstable, that's blue smoke. You don't need that to answer the question, because the question gives you the mass number and you look up the atomic number. Then this is the isotope we're talking about. And the question is, how many protons, how many neutrons? You look at the answers, you can see that. We're looking for the number of protons, 75. The number of neutrons would be equal to the difference there. 110, right? So we look down deep, 75 protons, 110 neutrons. Okay. I hope this isn't sounding like a Peanuts cartoon. You know, wah, 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 wah. That would be unfortunate. 22. Which among the following represents a set of isotopes? Atomic nuclei containing. Okay, so we've got 5 Roman numerals there with several isotopes. If we're going to pair them up as sets of isotopes, they have to have the same number of protons. Right? It's got to be the same element to be an isotope of an element. So if we look at 1, it's 20 protons and 20 neutrons. Who else has 20? Roman numeral 4 with 22 neutrons. So 1 and 4 is one of our pairs. 1 and 4. Then we look at 21 protons. We also got 21 protons down below. 2 and 5. That's another pair. So the only one we got left is 22 neutrons and 18 protons. They flipped it backwards, try to confuse you. 18 protons, there's nothing else in there with 18 protons, so it doesn't have an isotope in that list. So the only 2 you have is 1 and 4, 2 and 5, which is D. Okay. Let's see, 28. A species with 12 protons and 10 electrons is. Okay, it's got 12 protons and 10 electrons. Is it neutral or is it an ion? It's an ion, right? We're not balancing the charges. If that's 12 protons, 12 positives and 10 negatives, it has a 2+ charge on it, right? It's got 2 extra pluses. Okay. Now, we can tell what that X is if we look at 12. Where's 12? 12 is magnesium. And we know magnesium now has a 2+ charge. So we look for 2+, that's C. Okay. Magnesium with 2+. Okay.
We'll have access to a periodic table, right?
Oh, yeah. Yeah. Anything that's in the review document, they look in useful information at the very end. Anything that's there will be on the exam. Okay. That was 28, 29. The number of protons, neutrons, and electrons in 19 potassium ion 39. Okay, so the number of protons is 19. The number of neutrons is 20, right? 19 from 39 is 20. The number of electrons would have to be one less than 19, right? Because we have one excess positive, electrons have to be one less negative. So that would be E, should be the answer. Right, squirreling down some more. 33. Which of the following are incorrectly paired? Right. What this one is trying to do is to get you to recognize that the periodic table is subdivided into not just into single groups, but to some of those groups have names, and some regions have names also. So is strontium an alkaline earth? But we look, there's strontium in the second column. Yes, that's an alkaline earth. So A is correct. Ta, tantalum. Where do you find tantalum? Well, I didn't have you memorize that one, so you have to look it up. So you have to find it. So tantalum is 73. That's a transition metal. That's correct. Fluorine, you shouldn't have to look at that one. That's a halogen. H, is H hydrogen's a noble gas? No. Don't try to tell that to survivors of the Hindenburg. Right. It went up in just a few seconds. That whole balloon was gone. Because hydrogen is very reactive. It's not a noble gas. So we found our answer D. Ruthenium, Ru, you can find Ru in the transition metals. So D is the incorrectly paired one. 34. Which of the following is incorrectly paired? Okay, so now we're going to see if you know the symbols. Phosphorus, PR. No. Phosphorus has a single P. That's it. What is PR? PR is down 59. Praseodymium, I think that one is. You don't have to memorize that one. So the rest of them should be correct, right? Like lead, PB. Why is lead PB? Because it's Latin. PB stands for plumbum. And that's one of my favorites. Plumbum in Latin means heavy. 35. Which of the following is incorrectly paired? Okay, we got some more. Is copper Cu? Yeah, Latin for cuprum. Carbon. Yeah, carbon claimed the single C, right? Because it came before everybody else. If you came after carbon, if you were discovered after carbon, then you had to go to two letters. And remember, it's always capital small when you have two letters. Cobalt. Yep, that one's right. Calcium. Yep. Cesium. No. Cesium is CS. What's CE? I don't think you had to memorize that one. CE is cerium. Cerium's down here somewhere, I think. There it is. 58. All right. 36. Which of the following are incorrectly paired? Okay. Antimony, is that right? Yeah. Antimony is stilbium, Latin. Silicon. Yep. Si. Silver, Ag. Latin for argentum. Argon, Ar. Yep. Astatine, As. What's As? Arsenic. Arsenic. Astatine is At. It's down here. And it's a halogen. It's also radioactive. Whenever you see these square brackets, that's the most stable radioactive isotope of that element. Right? If you see that, that means it has no stable isotopes. That's the most stable. Okay, 37. All the following characteristics of metals except. All the following are characteristics of metals except. Good conductor of heat. Oh yeah. Malleable. That means you can twist it and shape it. Yeah. Ductile, which is kind of like malleable, only ductile means you can stretch it into a thin wire. Yep. Often lustrous. The reason we say often is because metals that are precipitated from a solution in very finely divided form are black. And they only become shiny when you polish them, or if you get enough of them deposited on the surface so they start to blend together. Like Christmas tree bulbs. Right? They coat the inside with silver that's precipitated from a solution. And it takes a while to build up enough of it to get shiny. At first, it looks black, and then over time, you deposit enough to make it lustrous. And E tend to gain electrons in chemical reactions. Metals are the other way around. Metals tend to lose electrons. They want to form positive ions. All right. Down 41. All right. You're given a compound with the formula MCl2. What's M? A metal, right? There are no elements up there with just M. Well, it says in the problem there. You are told that the metal ion has 26 electrons. 26 electrons. What is the identity of the metal? Okay. When we have a metal nonmetal, and the nonmetal is chlorine, what is chlorine's charge going to be? -1. Right? If you look at the periodic table, no charge, -1, -2, -3. Okay, so chlorine's going to be a -1 charge. That means it has a total of 2 minuses that have to be balanced by that one metal. So the one metal must be 2 plus in order to become neutral. Right? Okay. So with a 2 plus charge, how many protons does it have? 28 protons, because we were told it had 26 electrons. Okay. Now 28 protons, you go straight to your periodic table, find that it's nickel. Okay. They just ask you for the metal, so E is the answer. All right, 45. Oh, before I forget, these extra credits, exercises, I think we've got 2 of them for this exam, like periodic table and name that compound, right? Okay. We also have 2 crossword puzzles, chapters 1 and chapter 2. Those in the past, I've been more lenient. I'm not going to be this semester. The deadline for those is midnight of the day of the exam. You can either turn them in during the exam or before, or you can turn them in, you can submit them in Brightspace before midnight. After midnight, that little thing where you get the documents and you submit them is going to disappear. The reason I do that is because I've had students in the past, far too many, who wait toward the end of the semester, find that their grades are in the tank, and they try to make it up with extra credits. The purpose of these extra credits is to help you learn the material. And if you go to the end of the semester and you haven't learned the material, then there's no hope for you. Extra credits are not going to do you any good for mastering the material. So I decided to stop that. Barney would say, nip it in the bud. No Andy Griffith Show fans in here? No? Okay. As I get older, those TV and movie references become more and more irrelevant. How many oxygen atoms are there in one formula unit of this compound? Well, you've got phosphate, which is a polyatomic ion, and it has 3- charge. So you have 2 of these groups required. Why? Because this is a 2+ charge, which means it has 6+ total. This has to have 6+ total. So 2 times 3 minus, oops, sorry, minus. So how many oxygens? 2 times 4 is 8. 8 oxygens in that formula. Okay. It's important to know how to do that because very soon we're going to have to determine the molar mass of that unit. And the way you do it is to count up the masses of each of the elements in there. So we know we have 8 oxygens. That would be 8 times 16 would be the contribution of oxygens to the total. Right. I'm just giving you a taste of the future. Okay. 45, 47. Now we're going to name compounds or write formulas from names. What are the 2 rules that naming conventions have to follow? Unambiguous. When you got a name, you can't have anything but one formula for the compound. There's no choice. It's that one or it's nothing. Or if you have the compound formula, you can get the name from it and no other name but that one. And the second one is non-redundant. You don't repeat yourself in naming. We'll come to one in a minute. 47. The correct name for FeO. Okay. First of all, is that a metal nonmetal or a nonmetal nonmetal? Right. We're trying to decide type 1, type 2, type 3. It's a metal nonmetal, right? So it's either a type 1 or a type 2. What's the difference between those two? Can the metal have more than one charge? In this case, it can because it's transition metal, and it's not one of these. Silver, cadmium, zinc only have one possible charge, so they would fit in the type 1 bracket. But the rest of them, like these, all the way through the transition metals, have multiple charge possibilities. They're type 2 compounds when they're in metal-nonmetal arrangement. So how do we find out what the charge is? Because that's needed for the name. Well, oxygen is a chalcogen. It has a 2- charge when it's in an ionic compound, right? -1, -2. So if that's 2-, this has to be 2+ because there's only one of them. So the name would be simply iron, state the charge, and then oxide. That's the name. Okay, unambiguous, non-redundant. 48. The correct name for Ca2 plus. All right. We know the symbol is calcium. And we see it's an ion. Do we have to say what charge it is? No, that would be redundant. Alkaline earths only have one possible charge, 2 plus. So calcium ion is the correct. And notice we stuck calcium 2 in there, calcium 2 ion, just to see if you know that fact. All right, 51. Make some room here. Also, my habit is, since I'm recording this, if we run out of time, then I'm just going to keep talking and finish the recording, assuming I have time and I don't have to be someplace else. But if you have to be someplace else, you can pick up and go at 1:45. But I'm going to finish the recording so I can get it posted in the right space. 51. And if you don't have any other place to be, you're welcome to stay. What is the subscript of barium in the formula barium sulfate? So we know barium, right? Sulfate is a polyatomic ion with what charge? 2 minus. Always 2 minus. Right? It's in that list, and it's in useful information. Barium is what? Barium is alkaline earth. So it has what charge? 2 plus, right? Alkaline metal, 1 plus. Alkaline earths, 2 plus. Aluminum, gallium, indium, and boron, 3 plus. Okay, so what's the subscript on barium? Well, we only need 1 of each. So the subscript is understood to be 1. We don't write it there. That would be redundant, right? If the symbol's there, there's got to be at least 1. So the subscript is 1 for barium. How about 53? The formula for sodium dihydrogen phosphate. Okay. Sodium and dihydrogen phosphate is a polyatomic ion. Oops. Sulfate, phosphate. What's the charge on it? Well, if you don't remember, look it up in the list, right? It would be a -1, wouldn't it? I look at it this way. Phosphate is 3 minus. Monohydrogen phosphate would be a positive taking away one of those, would be 2 minus. Dihydrogen phosphate is 2 positives taken away 2 out of the 3. You only got 1 left. Okay. So if that's a 1 minus, that's a 1 plus, that's it. That's all you need. Because this acts as a single unit, right? That negative charge is spread over that entire polyatomic ion. And by the way, polyatomic ions are bound together covalently. They're very strongly bound. And any charge that they have is spread over the entire molecule. Or the ion, excuse me. All right, so that would be the correct formula. All right, A. A would be the correct formula for that named compound. (56) All the following are in aqueous solution. Okay. Acids. This is the one where we didn't. Well, I had to tack on. Right, we didn't finish the acid discussion, right? So I had to tack it on to the end of the video, and you had to go back and look at it. So the naming conventions for acids, right? What's the first rule when you're looking at how to name an acid? Well, first of all, it's got to have at least 1 hydrogen in the front. It can have other hydrogens out here, but it always has to have the acidic hydrogen first. 1, 2, or 3. That's the most I've ever seen, just 3 hydrogens. And then it has the other part of the molecule. So what can the other part of the molecule have or not have? Oxygen, right? If it has no oxygen, like that one, and you put it in aqueous solution, right? If it's not an aqueous solution, we would name it hydrogen chloride, right? Yeah, and it would be a gas. But if we bubble it through water, dissolve it in oxygen, makes the acid. That would be hydrochloric acid. No oxygen means you start the name with hydro, and you change the ending of "ide" to "ic," hydrochloric acid. Okay. Now we've got this 56. We want to find the one that's incorrectly named. So H2SO4 in aqueous solution is derived from hydrogen sulfate. Right? And 8 become X. But you don't say hydro because there's oxygen there. So we say sulfuric acid. That's the first one. That was correct. Carbonate. H2CO3. There's oxygen there, so we don't say hydro. We just change that 8 to ic. Right? Carbonic acid. That's what you swallow when you're drinking pop. Carbonic acid. Phosphoric. Right? Phosphate. Right? Oxygen, so we don't say hydro. 8 becomes ic. Actually, for aesthetic purposes, we don't say phosphic. We say phosphoric. Phosphoric acid. Right? For the third one. That's correct. HCN. HCN. Right? There's no hydrogen, so we say hydro. And cyanide becomes ic. So we say cyanic acid. Hydrocyanic acid. Nope, that's wrong. It's not cyanic, it's hydrocyanic. And then hydrochloric, we already did that one. That one's correct. Okay. That one tends to give students trouble because we had to, this comes out of the Middle Ages, alchemists. They started naming these acids before we standardized them. So the IUPAC committee that's responsible for naming had to sort of blend them together in such a way that they made sense. And that's what they came up with. All right. 59. Which of the following names is correct? Okay. So we got 4 examples, and we're trying to match the name to the symbol. Sulfide, S2 minus. Yeah, it's a chalcogen. Those are 2 minuses. So if we say sulfide, all we have to say is sulfide. That's correct. Actually, you could say sulfide ion too. Ammonium chloride, is that right? Ammonium is the only positive polyatomic ion in the list that I gave you. It's a +1 charge. Chloride would be a -1 charge because it's a halogen. So ammonium chloride would be correct. Acetic acid. Here's one where you have hydrogen out front, and we have to assume that this is aqueous also. We have a polyatomic ion here, which is acetate. and H become X. But there's oxygen there, so we don't say hydro. We just say acetic acid. This is the acidic hydrogen. That's the only one that dissociates in solution. These three are bound too tightly. We won't give them up. So that's why we put this one out front. Okay. Barium oxide. That one correct? Yeah. Barium is an alkaline earth, +2 charge. Oxygen is chalcogen, -2 charge. 1 and 1 is all you need. Barium oxide. So all of them are correct. That acetic acid, you may see it written that way, which is the molecular formula, or you may see it written this way. Let's see, CH3C. C2H3. That's right. This gives you a little more structural information. That's all. Right. And this is the hydrogen that dissociates right here. These three are bound to that carbon too tightly. You're not going to have to remember that for a test. I just say, if somebody ever draws it, then you'll recognize it. Or you can impress people at parties, whatever your taste is. 61. All right, we've got a table here with some information that's already given, and the information in red in the blue squares is what we have to deduce. So if I can put this together really quickly. Symbol, number of protons, number of neutrons, number of electrons, and net charge. Okay. See, we have 4. Halfway, and there we go. So the information we're given here is 206 EB and Mn 2 plus. And then we're given 31 here, 52 there, 38 here, 75 there, and 30 here, 54 there, and 3 plus here, 2 plus here. Okay. Use a different color. See if I got something that's distinct. Purple. Okay. Let's take the easy part first. Is there any charge on that? Nope. No charge. Okay. So, how many protons? I have to look them up. Lead, 82. Now we can calculate the number of neutrons. Well, electrons would be the same, right? If it's going to be neutral. 82 from 206. Well, yeah, 124. How about this one? What's the symbol? 31. Gallium. Okay. We've got protons and neutrons, so that's 69. Is it charged? Yep. Got a 3 plus charge. That means the number of electrons has to be 3 less than that. 8. Okay. How about this one? 52 protons. Tellurium. Is it charged? Protons, electrons. It has 2 extra electrons. Okay. And its mass number is 127. So it has a 2 minus charge here. Okay. Manganese. How many protons? We'll go over there and look it up. 25. Okay. And the mass number on that would be 55. But you don't have to put that in there because there's no space for it. How about electrons? Well, it's a 2+ charge. That means we have two too many positives. That means we have 23 electrons. Okay? So you fill that chart out. 62 would be similar. Right? You've got the same sort of information in a different format. And I think you can do that on your own after you see how it's done. And in the interest of time, we're going to skip that one. I'll just leave it up there long enough to get it recorded. Now we want to do our symbols. More symbols. We've done a few of them already, huh? 63. Oops. Okay. First one, silver. We know it's argentum. Calcium. Iodine. Copper. Cuprum. And phosphorus. Okay. That's just memory. I probably don't. Well, just for completeness, I'll do them anyway. 64. We want to write the names for these formulas. FeSO4, right? Type 1, type 2, type 3. It's either a 1 or a 2, but it's got iron in there, right? It's multiple possible charges. That means we have to say what the charge is. So we calculate the charge based on that polyatomic ion, which is a 2-. This is a 2+. So we would say iron and the charge and sulfate. And you don't have to change the ending of polyatomics. They're fixed. Sulfate. Okay. NaC2H3O2, recognize that as an acetate polyatomic with a 1- charge. Right? And it's a type 1 compound because the metal is alkali metal. It's a fixed charge, only +1. That's it. Sodium acetate. KNO2. We know K is potassium, fixed charge, right? So it's a type 1. And NO2 is nitrite. NO3 is nitrate. NO2 is nitrite. They're both 1- charge. So we balance potassium nitrite is type 1. We don't have to say what the charge is. Calcium hydroxide would be the next one. Calcium is a 2+ charge, alkaline earth. Oxide is a polyatomic ion with a -1 charge. So that's why we have 2 of them there to balance the calcium. And we only have to say calcium hydroxide, right? If we said calcium 2 hydroxide, that would be redundant. And it would be, incidentally, it'd be wrong in the test. NiCO3, nickel. Yeah, nickel can have more than 1 charge. So we have to deduce what it is. Carbonate is a -2 charge. It's polyatomic. So nickel has to have a +2 charge to balance. That means nickel 2 carbonate. Yeah, that was on our list. Okay. Nitrate ion. That's not right. I can't see all of it. Nitrate should be. I better not mess with it because I can't see what the rest of it is. The nitrate should be 65. Nitrate should be NO3-. Okay. And you can just look that up in the table. Aluminum oxide. Okay. Aluminum is a fixed charge at 3+. Oxygen is a 2- fixed charge. So how do you balance an odd and an even? Cross multiply. Bring the 2 over here, bring the 3 over there. That gives you 6 pluses and 6 minuses. Ammonium ion, just look that one up. NH4 with a +1 charge. Perchloric acid. We know it has oxygen in it. So we look perchloric is derived from X come from 8s, right? In acid naming convention. So this would be perchlorate ion. We look up perchlorate ion, it's ClO4 with a minus charge. All we need is 1 hydrogen to balance that minus charge. So HClO4 is perchloric acid. Okay. If you ever want to cause havoc, you got a bottle of concentrated perchloric acid, which I think is about 70%. You just get you one of these tall beakers and put a nice big chunk of butter in it and set it on your hot plate under the hood and pour pure perchloric acid on it. Right? You don't even have to put a cover glass on it. This is not going to help any. And then turn the hot plate on high, pull the sash down, and evacuate the building because it will blow. Copper 2 bromide. Okay. Copper, yeah. Copper has the possibility of a +1 or +2 charge. So it's a type 2 compound that we have here. Copper and bromide. We know that it's copper 2 because we have 2 bromide ions, and halogen's always -1. So that's a 2- total. This one has to be a 2+ to balance it. So we write it copper 2 bromide, type 2 compound. Okay. Now we're going to name compounds from their formula. Get rid of some of this ghosting. All right. I'm not going to write these on the board. We should be able to do these in our head. Aluminum and sulfate. Right. Aluminum is a fixed charge. Right? It's a 3+ charge, always and forever. Sulfate is a polyatomic ion with a 2- charge. Right? So all we have to do is say aluminum sulfate. That's it. It's a type 1 compound. Ammonium nitrate is also a type 1 compound because the position of the metal is occupied by a polyatomic with a fixed charge. Right? So ammonium is a +1 charge, nitrate is a -1 charge. We only have to say ammonium nitrate. Right? And then add 6% fuel oil and a blasting cap, and you got a nice bomb. 68, NaH. Normally, when hydrogen comes first, it carries the +1 charge in a compound. But if it comes second, then the metal has the fixed charge. Sodium has a fixed charge of +1, and hydrogen now has a -1 charge. So we treat the hydrogen as the anion in the compound and change the ending to IDE. That's why it's sodium hydride. All right. K2Cr2O7. Cr2O7 is a polyatomic ion. You can look it up in your table with a -2 charge. Right. Potassium is an alkali metal with only a +1 charge. That means it's fixed, so it's a type 1 compound, and we say potassium dichromate. Cr2O7 is dichromate. Now, CCl4 is a type 3 compound, non-metal, non-metal. So how do we name those? We can't balance charges because there are no charges. Non-metal nonmetals are always covalent compounds. So we just say, how many carbons are there? Well, if there's only one, we don't say mono. Not for this position. And then we say chloride, but we have to say how many there are because we can't deduce from the formula how many there are. So we use the Greek prefix for 4, which is tetra. Carbon tetrachloride. Right? That's what we used to use to dry clean clothing. Put your clothing in a big stainless steel drum and dump a bunch of carbon tetrachloride on it, spin it around for a while, and then drain the carbon tetrachloride off and hang it up for the traces to evaporate and the workers to inhale it. And then it cleans without damaging the fibers. We don't use it anymore because it was implicated in various health hazards. We use substitutes for it. It's a very effective dry cleaning agent, but unfortunately, it's not good for the workers. Okay, AgCl. Type 1, type 2, type 3. Metal, non-metal. It's 1 or a 2. It's a fixed charge. Silver is always +1. So silver chloride is all you need. That names the compound. Calcium sulfate. Sulfate is a polyatomic with a 2+ charge. Calcium is a fixed charge, 2+, alkaline earth. So it's a type 2 compound. Type 1 compound, excuse me. Type 1 compound. And we have to assume HNO2 is in aqueous solution. That's why I gave it nitrous acid. Right. We don't start with hydro because there's oxygen there. And nitrite with a hydrogen in front in aqueous solution, the ites become us's. So it's nitrous acid. N2O3, type 3 compound, right? Non-metal, non-metal. Now we say how many nitrogens there are. Dinitrogen, trioxide. Tin has the possibility for more than one charge, so we deduce the charge from the fact that iodine is a -1. There are 2 -1s, so that's 2 minuses. The 110 must have a 2+ charge to balance. So it's 10-2 iodide. Let's see. Oh, we're going the other direction now. We want to run out of time. We're not even out of chapter 1 yet. S2O3 is thiosulfate with a 2- charge. So sodium thiosulfate is all you need because type 1 compound, sodium is a fixed charge. Iron 3 oxide. So when you say iron 3 oxide, we know we have iron, we know we have oxygen, and this is a 2-, and this is a 3+ because the name tells us it's a 3+. So we have to cross multiply, Fe2O3. Dichlorine heptoxide. That's simple, right? It tells you how many of each. Cobalt 2 chloride. We know what the charge of cobalt is, 2+. We know chloride is -1. So we need 2 minuses to make up that 2+. Aluminum hydroxide. Aluminum is a fixed charge at 3+. So hydroxide is a -1 polyatomic. That's why we need 3 of them, and you have to have the parentheses. Polyatomics cannot be split. Right? If you need more than one polyatomic, You have to use parentheses. Why? Because the charge doesn't belong to any one atom. It's over the entire amount. So parentheses are required. Sulfurous acid, SO3 is sulfite. Ites become us. So SO3 is derived, sulfurous is derived from sulfite. SO3 2 minus, you need 2 hydrogens to balance it. Nitric acid, phosphoric, we've done those before. Acetic, we've done that one before. Oh, that's another way to write it also. Instead of writing out the formula, you could do this. Right. This is the carboxylic acid group, right? That gives you the acid hydrogen. That's one way to write it, or you can write it out, HC2H3O2. Phosphorus trichloride, 1 phosphorus and 3 chlorines. Okay. Law of definite proportions, D. The percent by mass of iron in galena is the same for all pure samples obtained from any source. Law of multiple proportions. We've done this. We've looked at multiple proportions before, so I'm not going to go into this one. Just let you know that B is the answer. Which of these doesn't have the symbol that's derived from Latin? Fe, Cu, Na, K. Titanium is Ti. They can be derived from the English name. Which of the following ions is not likely to form from the appropriate atom? Okay, well, we'll do this. Carbon 4 plus. Is that possible? It's possible. That's why we say likely. Let's look at the others and hold that one in reserve. This one could be a problem. Arsenic, 3 minus. Where's arsenic? Here, right? -1, -2, -3. Yeah, that's a good one. Magnesium, alkaline earth. Second column, 2 pluses, all of them. Titanium, 4 plus. You can look at your periodic table, look at titanium. It has possibilities +2, +3, and +4. That'll give you that answer. Sodium, alkaline metal, +1, always. C4 plus is the least likely to form from these, but it does happen. I think that's why the wording is that way. All right, how many protons, neutrons? I'm going to skip that one. We've done one like that already. Similar to 94, we've done that one like that. Naming compounds. In the interest of time, I'm going to have to skip those. So then we go down to, oh, wait a minute. What happened? Did I miss the transition? Did I? There's chapter 2. Oh, I did. I skipped right over 1, didn't I? My apologies. Right, we're out of time. Well, I'll tell you what. I can just give you the answers. And then you tell me if they don't seem right. There are also archived videos that are in proper order. So we have D and D for the first 2. That's basic science stuff there. know what your prefixes mean so you can tell if these are the correct order. Unit conversions. All right, if you have 8.1 kilograms, how many grams is that? 8.1 kilograms. You can do it two different ways. You can do unit conversions, right? So that'd be 1 kilogram is 1,000 grams. So that's 8.1 times 10 to the third grams. Okay. Or you can say, what does kilo mean? Kilo means 10 to the third. There you go. Convert meters to millimeters. Does anybody have any trouble with dimensional analysis? Because we're going to use it a lot. Unit conversions. Difference between mass and weight. Does this represent accurate and precise measurement? Well, if we look at the plus or minus, right, the first trial is somewhere between 1.200 and 1.202. And the second one is 02 or 00. So those are accurate measurements. Are they also precise? Well, why does it say precise but inaccurate? Precise means that they're grouped. But inaccurate. Oh, I didn't read the problem. We know the mass is 1 gram, right? If it says, if we're measuring 1.2 grams, that's not accurate. Okay. Now it makes sense. Let's see. Know how to round to the proper significant figures. You got to know your rules for significant figures, right? All non-zero numbers are significant. Then you go to zeros. Preceding zeros are never significant. Captured zeros are always significant. Trailing zeros are only significant if there is an explicit decimal in the number. So this number, as written, has 2, 4, 6, 8 significant figures as written, but we want to reduce it to 4. So where do you start counting? You go to the 4 on the left and count to the right 4 places to that second zero. Then 6 is greater than 5. That means it's 0.04501. Would be rounded to 4 significant figures. Now, why did you let me do chapter 2 and not 1? Huh? You're supposed to keep me in order. That's the job of a student. Keep their instructors from flying off on a tangent. Let's see if I can find an example of something that might give you trouble. How about this one? What's the best answer to report for this one? 32. All right. What's PEMDAS? Parentheses, exponent, multiply, divide, add, subtract. So do we have any parentheses? Yeah. 3.478 times 1.164. Where's my calculator? We will go over a little bit. So 3.478 times 1.164 is 4.048392. But we also have a divide, right? Before we get to the minuses. We have a divide. We have parentheses, skip that one, skip that one. Now we have a divide in order. So what you can do is you can take the multiply and divide first, and then round that one. That helps you eliminate rounding errors. So I'm going to go ahead and divide by 2, right? And that gives me 2.024196. And then I can round to how many significant figures determine multiply divide? 3. 2.00 is only 3 significant figures. The others are 4. So we're limited to 3. Here. That's less than 5, so it goes away. So now we have 2.02 minus 169, 0.169. Line up your decimals, and 9 from 0 is 1. Now I'm going to do it by hand. 6 from 11 is 5. 1 from 9 is 8, and then 1. Plus. Let's see if I did that right. 0, 12, 10. Yeah. Okay, how many can I keep? Right there. So rounding that one, the answer is 1.85. C is your answer. Okay. We had to separate them based upon PEMDAS and different rules for multiply, divide, add, subtract. Let's see. Okay. I saw one that might give you trouble. No. We'll probably get to it. These are all worked out in work problems too. This is an interesting one. 56. It requires that you think of a cylinder. Only this cylinder is a half-inch, well, not actually, but like a half-inch deep and 3 miles wide. Okay. A mono layer containing so many grams of oleic acid has an area of 20 square centimeters. So how do we get that? You have water and you have oleic acid, which has a hydrophilic end and a hydrophobic end to it. So the hydrophilic end here is going to be attracted to the water, and the hydrophobic is going to stand straight out away from the water. So that's the depth of your cylinder, however long that chain is. So we've got a cylinder now with this depth, which is the height of the molecule turned on its end. The area inside that cylinder is 20 square centimeters. Okay. What we want to find out in order to determine this height is solve the volume, which is height times area for the cylinder, right? Everybody knows that from geometry. So we need to find out what the height is. We know what the area is, so we can find out the volume. Actually, we know the volume. The density of oleic acid is 0.895 grams per milliliter. How do we find the volume? Density equals mass divided by volume. So volume is going to fit in here once we find out what it is. Mass divided by density. So the mass of that oleic acid was given as 3.23 times 10 to the minus 6. 10 to the minus 6 grams. And the density is 0.895. 0.895 grams per milliliter, which is cubic centimeters. Right? 1 milliliter is exactly equal to a cubic centimeter. So if we divide that into that, grams cancel, and we get volume of cubic centimeters, right? Stop me if I lose you. Exponent 6.895 divided. So I get 3.6089. I'm going to keep a bunch of decimals here because we don't have any add subtracts. I'm going to keep them till the very end. And this is cubic centimeters volume. Okay, so this one is going to fit in right here. And the area is 20 cubic square centimeters. We can solve for H. So H is going to be volume divided by area. Volume is 3.609, 60894 times 10 to the minus 6 cubic centimeters divided by 20 square centimeters. So the height is 1.80447 times 10 to the minus 7 centimeters. And since we've only got 3 here, we can say 1.80 times 10 to the minus 7 centimeters is the length of that molecule. Okay, so that's D. All right. I'm looking for ones that might give you trouble. This picture, that one might give you trouble because you got to understand what they're trying to represent with that picture. Each circle, each square is an atom, right? For 70 through 73. 70 through 73. Each one of those is atoms. So if we're looking for 70 is a mixture of an element and a compound. You want separate circles or separate squares as one of them, and a combination of 2 or more for the other one. So a homogeneous mixture would be uniform throughout, and it would have circles and squares. That's why E is the best answer, right? It's got squares and 2 circles, one clear and one shaded. Gaseous compound. Compound. Which one's a compound? And a gas. A and C are gases because they're so far apart. And the only compound is C. All right. And the last one, next to the last one, solid element. Solid's going to be packed very close together, and it's going to be uniform with exactly the same atoms in each one. That's why B is the answer for that one. And which is the best heterogeneous mixture of 2 elements? Right? Can't have any compounds. Right? And they have to be a heterogeneous mixture, non-uniform throughout. 2 elements. How about D? Circles, both circles, one of them shaded, one of them's not, and they're not uniformly distributed. That's probably a liquid, but it doesn't have to be. Okay. That's it.